Hi, today I'm going to start to talk about the friction, and we'll go over some introduction about the friction and how we can use the friction when we are working with the statics case. In other words, how we handle friction from the statics point of view. To start about friction, first assume we have a simple case. We have a simple box here, and then we will see that what will happen to that box. So assume there's a box here, and that box is sitting on the ground like that, and then that box is there's a force applying on that box. We'll say that there's a force, any force would be uh, apply on that box. It says that there's a force here, apply on that box, and then we will want to see in case of the statics what would happen. So I would draw the free body diagram of that box. So if I draw the free body diagram for that box, so I would put first the external forces I have. So the ones for external forces I have is the P, the force, I assume that's the force P. So I have that external force P apply on that. Then we know that there is going to be the W, the weight of that box applying there. And then we will have the reaction from the ground, so the normal forces is going to be there, um, and we have the friction, and the friction is always, remember, opposed the motion, and is in the tangent to the surface. So it's oppose the motion tangent to the surface, so it's going to be like that. So if I have to draw the friction, that's going to be, so that's going to be a friction uh, that we have. So basically, we'll replace the ground and assume the ground is the support. So we remove it and then we replace it with the forces. So the ground doesn't let this bar go down. So we replace it with the N, and the friction from the ground doesn't let the bar go to the right. So we replace it with the first to the left to hold it in place. Uh, if you look at that, you might notice that and there's a, if I go down here and assume this point O, there's a distance here between the W and N, and the reason for that is why the N is not going to be that. The N is the resultant force from the ground reaction, so it's going to be sitting there. It's not going to be right underneath of W. The reason for that is if the N is going to be underneath of the W, and assume we write the moment about point O. So the W goes through point O, the N goes through point O. If the N was underneath of O, it goes through point O, and then F is goes through point O. So none of the W, N, and the F would have the moment, and then the P has the moment about point O and cause the box to tip. So basically the N moves from O at the magnitude of X to the right or to the left, depending on the condition, to prevent that force P tip the box or rotate the box. Um, you know, so that's why there's a distance between N or this. So the moment from N about point O would cancel the moment that P created about point O. Now that we have this condition, there are three cases basically that we will have when we are dealing with the friction. The very first case is that there is no motion, so there is nothing move. And basically when there is nothing move is that whatever force we have here and the F here should be cancelled. So if I go ahead and write for this case, if there is no motion, it means that sigma Fx is 0. And if I look at that case, it means the P minus F is 0, or in other word, P is equal to F. So let me write it down. So In other words, P is going to be equal to F. So in that case, if there is no motion, uh, P and F, the F is exactly the same. So let's say, I would say that whatever value I have for the friction is the same as I have for the P. So if the force increasing, the magnitude of the friction increases. If the P goes down to zero, the friction goes down to zero. So it's exactly equal to that, as long as there is no motion. The second condition that might happen is that if we go ahead and then we have uh, we are on the verge of motion. There is no motion, but uh, on the verge of um, motion. So we are not moving, but we are about to move. In that case, if I say that, if you look at here, if there is no motion, as long as the P increase, the F increase, P increase, F increase, because they are equal. Now, if we increase P so much to the magnitude that is about to move, basically P is get to the value, the F will get to its maximum value, and in that case, the F would be uh, uh, F becomes maximum, and generally it would shows by Fs, and it's gonna be the mu s times n, and the mu times the mu s is the friction factor. And then is gonna be the third condition, if we're actually there is a motion. So if it's moving, in that case that is a motion and everything is moving, in that case the friction would become it calls it Fk, and it becomes Kn. These two cases, the first cases and the second cases, that I would say here we have, for these two cases, uh, I would say that's what we have. These two cases here, these two, when sorry, these two cases is, we will call it the static friction, because basically there is no motion. There's nothing is moving. Everything is stay there. There's a friction, but everything is stay there. Here, when everything is moving, we call it the kinetic friction. So basically, these two first cases, when there's no motion or on the verge of motion, is the static, and when there is actually a motion, we call it the kinetic. The other thing I want to mention, that here, if you look at here, if I go ahead and the resultant forces between, if I draw the resultant forces between N and F, uh, it will produce the angle, that this angle would be called phi. If I write the phi here, the phi value is basically tangent inverse of F over N. And if you look at F over N from these two equations, if you look at the F over N is equal to mu F over N. F divided by N is mu. The same here, F over N is divided by mu. So therefore, the phi would be tangent inverse of mu. And in some area, in some courses, uh, mostly when they want to give the friction, they give this phi value. In some courses, it gives you the mu values. Well, so very easily you can just convert them. If you have the phi, and convert them to mu. If you have the mu, you can convert them to the phi. Now let's look at these and see how these would behavior if I'm looking at them on a graph. So if I have my box again, draw the box again and say, okay, this is a box I have, and then the forces applied on that box is the P, W, and there's going to be the N and F. Now if I go ahead and uh, draw them as I want to draw the friction as a function of P. See what happens. We know that when the P value is small, for the small value of P, we know that the friction uh, is equal to P. That's what we have it from when there was a no motion, F and P are equal. So basically, when the P is small, there's no motion, and P and F are equal. So the P and F would be equal, and they would be 45 45 degrees angle here. So it goes up there and the same. So in this area would have the uh, F is equal to P. And then eventually it goes and it reaches to the verge of motion when it wants to start to move. And when it gets to the verge of motion, it's the point that it reaches its maximum value. And when it reaches its maximum value, it becomes equal to Fs. We know the maximum value of the friction was Fs, so it was increasing, 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 it gets to the Fs. And eventually when it gets to the Fs, uh, it gets to the verge of motion, and by the time it gets to the verge of motion, there is a drop here, and then it becomes constant, almost constant. And in that case, when it becomes constant, is where uh, uh, so that's the maximum one, and that's the, if I want to, that's the constant part. So here is the part that there is no motion. Here is the part that there is a motion. And when it gets to that motion part, that value, so this one is going to be, this value is almost constant and is equal to Fk. And we know that the Fs was is mu s times n, and Fk is mu k times n, and we know that the Fk is always smaller than Fs. And that point here, is right on the verge of motion. It's where it would start move. So if you are in no motion zone, uh, basically when the p is very small, the f is equal to p, that it goes up way, up way, up way until if the p is increasing, 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 it eventually get to that uh, peak here where it's about to start to move, and when it start to move, it drop down, and the friction almost become constant from that point on. That would So these are basically what's what we have for the theory. Now let's look at that how we will use them if we want to solve them in let's say statics. So let me so when it comes to aesthetics point of view, there's three cases we might have. So again, the very first case is that we know that the first case there is no motion in any contact point. So there's no motion anywhere in whatever we have. So for example, assume that uh, we would have an object sitting like that. So and sitting like that on the ground, and then if we have the let's see, we have the ground sitting like that, and then we have the point A and point B. So point A and the point B, and assume we know that it's not gonna move. Assume that under the condition when we have, it's not moving. For certain we know that it's not moving. If it is not moving, what we would have is that we will go ahead and replace the mm, contact A and contact B the same as it is as what we treated the reaction, the support. So we just replace them with the reactions at point A and at point B. So if I go ahead and I draw that again, so if this is our shape, so if you have it like that, and then the point A and the point B, so we can go ahead and replace, put the reaction. So we know that at point A there is a N A, and the point B there is a NB, and then we know that for friction we will have two frictions, so there's the FA and there's the FB. And in that case also we don't need to be much worried about the direction of these FA and FB, because everything is static. We will solve that. We write a sigma of x, sigma of y, sigma m is 0. Solve the insanity. If the FA FB comes negative, it means that the direction we assume was not right. So as long as it's not moving, we know that nothing is moving. uh, what we have is just the simple static case. Just replace the contact, the surface at the contact with the normal force and the friction, and then solve it like any other static cases that we will work with them. The second one is if there is a motion. What if there is a uh, if all contact all contact are on verge of motion. If all contact is on the verge of motion, what would happen in that case? So now assume again, this time I have something like that, and then I know that all if it starts to move, so it's again it's the point A and point B. So it's the point A and point B. Know that if this starts to move, if it becomes on the verge of motion, both A and B start to move at the same time. So all of them would be moving at the same time. In that case, again, if I draw that, in that case, we'll simply go ahead. We draw the free body diagram of that object. And then if we have the A is here, and B is here, and the B is here, and then we put a reaction on that. We're gonna have the NA, and then we know that in this case it's gonna move to the left, so the FA is gonna be to the right. In this case, it is important that we get the direction of the friction correctly. If it's on the verge of motion, if any kind of motion is involved, it's really important that we get the direction correct. Here the same, here is the NB, and it's going down, it's going to move down, and therefore the friction is going to oppose that upward. So we know that the friction is always oppose the motion, so it's going to be upward. The difference between this case and the previous case is that here we know that the FA is going to be because it's on the verge of motion, is going to be mu s NA, and the FB is going to be mu s NB. So we know the magnitude of that. In the previous case here, we know that the FA is going to be smaller or equal to Fs, because there's no motion, that's not on the verge of motion, and the same, the FB is going to be a smaller to Fs. But in this case, they are equal because it's on the verge of motion, and both of them are on the verge of motion at the same time. The third case that we might have is that only some of the contacts, for instance, some of the contacts are on the verge of motion. In other words, part of that, some part of the what we have might move, some part of that might not move. Now let's look at again the first case, but this time assume that, for example, we have something like that, and then we have something like that, and then assume this time we have the ground is here, and there is some forces, assuming applying on that. So we have the one force applied here, and then we have point A, and we have point B. In this case, we know it's gonna move, but we don't know either A is gonna move first or B is gonna move first. When we don't know if A is gonna move first or B is gonna move first, in this condition, when we are on the sum of that, we will have to consider a couple of cases. So assume here the question is that what's the maximum value of P that none of the A or B is gonna move. So we know that if we're gonna increase the P, increase the P, eventually one of the A or B is gonna start to move, but we don't know which one is gonna start to move. So in that case, first we have to consider, we have to solve for the entire problem for as many cases we have. For example, in case one, what we are going to do that, we will assume that is the case one. In the case one, we assume A sleeps first. So that A start to move first. What if the A start to move first? We know that A start to move first, B is not starting to move, so we know that the friction at A is gonna be equal to yes nk. That's what we know. And if I now I put the so we have here and A, and we don't have, if it's gonna move, it's gonna go to the left, so we have the FA, and on to in the B we have and B, and we know if it's gonna move, it's gonna go to the right, so the friction is gonna be FB, the others. So in the case one, what we have, we know is that this is the case. So we have the FA, so, and then we solve for all unknown, for unknown. And then, for example, in this case that we want to find what's the minimum value for the P that make this uh, start to move. So this is the case. We want to know what's the maximum value for P before either A or B starts to move. So we assume in the case one, we assume first A starts to move. So if A sleeps first, the A is gonna be become equal. So this one is not right. So um, so here is gonna be N. It's gonna be NA. So we can calculate the P, and it gives me some value. Then for the case B, the second case that we want to do is that we will go ahead and we assume B sleeps first. So that's what we want to do. The same here. So in the first case, we assumed that we assume the A is sleeps first, and in the second case we assume B sleeps first. So if we assume in the second case that A is not sleeping, actually B is sleeping, so in that case if B is gonna be mu S and N B, and then we are gonna solve for all unknown, and then we calculate the P. Then we compare the P we get from the first case and compare with the second case and see which one is smaller. That one is the one that caused these stars to move. So one more time, if I go over that, if we have something like that, and it says we don't know, not all, one of the contacts or some of the contacts move, some of them doesn't move. So like here, we know either A or B is gonna move. We don't know which one's gonna move. So we have to solve the entire problem once for the A, assuming A is the one that's gonna move first, and then find all the unknown you want to find. And then we have to go ahead and assume this time for the second one that the B is the one that's gonna start to move, not the A, and then solve for all the unknowns, and then we compare the case one and case two and see which one is the correct answer. For example, here we said that we want to know what's the maximum value of the P that cause either A or B starts to move. So in the case one, we will assume A sleeps first, so we can, because A is asleep first, so its friction becomes and the maximum friction, the friction at the work, and then we solve the entire body, and then we calculate P. Then we'll go ahead and say no, assume B is the one's gonna start to move first. So we, this time the magnitude of friction at B is the um, equal to mu S and B, and then we solve the entire case for that and we find P, and then we compare these two P values, and whatever is the smaller one is the one that caused that object moves first. So these are the three cases we will have. Again, one more time, if you have no motion, it's like whatever we have in all the static cases we had before. If all the contacts move together, then just replace all the friction with their maximum value, and make sure that you get the direction of motion and direction of the friction correctly. And the third one, if some of them move, some of them don't move, for everyone that might move, we have to solve the entire case once, and at the end we compare all of them together and see which one is the case that we are looking for. Okay, now let's look at the example. Assume we have a box sitting on the ground and there's a 300 Newton weight and there's a force applied on one end of that. And we have the friction factor is equal to 0.35. I want to see if this is in equilibrium or it actually it starts to move. So before work on that, we draw the free body diagram for that box. So if I draw the box here, and then we have the external forces on that, so it's going to be 100 Newton, and this angle is going to be 45. And then we have the weight lying on that, so it's a 300 Newton. Then we have the reaction also, the reaction for the support. So we have the n values, assume it's going to be there, so it's n, and we know that it's going to, this force is going to pull it to the right, so the friction is going to be oppose the motion, so it's going to be to the left, because the friction always oppose the motion. And if I go ahead and assume this point O, and this distance is x, and know the other distances we have, so it's going to be, the distance here is going to be 0.6, and this distance here is 0.4. Before I do the solution, I will go ahead and find these forces, so it's going to be, this one is going to be 100 Newton cosine 45 degrees, and this one is going to be 100 Newton sine 45. So this is our free body diagram. I will go ahead and write the equilibrium equation. So if I go ahead and write the sigma of x is 0, what I would have is that I have here 100 cosine 45 degrees is a positive here, and then it will cancel, and then we have the friction, which is going to be F0. Therefore the F value would comes out as a 7.71 Newton. So that's what we have for the F value. If I write the sigma Fy is 0, what I would get is that I have the n is positive, then I have 100 sine 45, which is also positive, and then I have this 300, which is going to be negative, and this would be 0, and therefore the magnitude for the n would comes out at 229.29 Newton. And then if I write the sigma m about point O, if I write the sigma moment about that point is 0, and assuming the counterclockwise is positive, then what I have here, the 300 Newton here goes to O, and the F goes to O, so they don't, because both of them pass through point O, they don't have any moment. Then I have this N that has a moment, and these two forces here that has a moment. So I would start from here, so I have the 100 sine, have 100 sine 45, so that's this force, and the normal distance between this force and point O is 0.6, times 0.6. And if you look at it, that one, this 100 about point O is going to rotate the object like that. So it's going to be counterclockwise, therefore it's going to be positive. Then I will write for this one, so I have the 100 cosine 45, and the normal distance between this one and the point O, this is the normal distance between them, is 0.4. That's going to be 0.4. And this one, if you consider about the point O, is going to rotate it like that. So it's going to be clockwise, therefore it's going to be negative. So it's going to be negative. And then I have the n. If I go ahead, so I have the n value, and the n, its normal distance is x, and about point O is going to rotate like that. So it's going to be counterclockwise, so therefore it's positive. That's going to be 0. And we know the magnitude of n from here, so we can just substitute this value for the n. So that's the value for the n. And if we go ahead and use that value, we will get the x, what comes out as a negative 0.061 meter. So it's basically, it says that the n is in the other side of the O, is got somewhere here. Now we have find this f, n, and the x value. Now we want to know that if actually it moves or not. So to know if it's move or not, we have to go ahead and calculate the maximum friction. So the f max is basically fs, which is going to be equal to mu(s) times n. So we know that the mu(s) is 0.35, so it's going to be 0.35, and the n is 229.29, which gives us 80.25 newton. So here what we have, we will see that, so because the fx is larger than the f we have, so basically what we have is the f is smaller than the fx, therefore there is no motion. So there's no motion, it does not move. Also, you look at here that this distance here, the x is smaller than the 1.2 over 2, because the x is between these lengths, so x is between this is the half of the length. So because the x is not outside this box, x is actually within the box, because x is going to be between 0 and 0.6. That's how much it's going to be. So because x is a smaller 0.6, is not going to tip. If we calculate and somehow we find that x is going to be larger than 0.6, then it will tip. So there's no tipping also. So there's no tip, as if x was there, assume the x was here or x was here, so it means that we then for the moment we need to balance the moment by this force is not going to produce here, but we have to bring the n outside the box. That's not going to happen to balance that force. Because of that box is going to tip and it's going to rotate. So also that's another thing, x is within the half of the length, is less than the half of the length, therefore there's no tipping. It's smaller than the fs, also there's no motion in this case, so it's gonna stay there, and there would be a balance there. Now let's look at another example. This time we have this rod sitting against the walls, and we want to know that what's the angle that this rod actually becomes on the verge of motion. So basically, if I move the point A toward the right. It keeps moving, moving, moving. At one point, it becomes unstable and starts to move, and it's not gonna be in equilibrium anymore. So in this case, we have both contacts at the same time. Both contacts would be on the verge of motion. So we'll draw the free body diagram for that rod. So if it's a free diagram that run, and then we would put the all the reaction and external forces on that. So for the external forces, the only external forces is the weight here on the center, so it's going to be 100 Newton. And then we have the reaction of the support. So we have here for point A, we have NA, and for the friction, we know that if it starts to move, it goes to the right, so therefore the friction should oppose that, so it's going to be FA. And for the point B, we have the NB, and we know that if it starts to move, this is moving down, so the F is opposing that, and it's going to be upward. So that's the free body diagram of what we have. And then we want to, if this angle is theta, if this is going to be theta, we will look at the distances we have. So also the distances we have here. If this part is 2.5, so if I draw that, so it's a 2.5, that's a 2.5. So therefore, this part is going to be 2.5 cosine theta, and the same as the other section, so it's going to be 2.5 cosine theta, and this length here is going to be 5 sine theta. Now if I go ahead and start to write the equilibrium equation, the very first equation I can write is the sigma of x is 0. And if I write the sigma of x is 0, what I have here is I have the NB in the positive direction, and I have the FA, it's going to be 0. For the sigma Fy is 0, I have the NA is a positive, and then I have the FB also is a positive, and then I have the weight, which is going to be negative. It's going to be 0. And then if I write the sigma moment about the point A, and this point is 0, and assuming the counterclockwise positive, so if I write it about this point, so I write it about point A, so FA and NA, both of them goes through point A, they don't have any moment because they both pass through point A, but the other forces has. So I will go ahead and write these other forces. So if I start with the NB, so I have the NB, and then the normal distance between NB and the A is 5 sine theta. And then also if you look at it, it's going to rotate like that, so it's going to be clockwise, so it's going to be negative. Then I have this other one, the FB, so the magnitude is FB, and the distance between FB and the A, the normal distance, is also this distance, the 5 cosine theta. It's from here to here, the 5 cosine theta. And again, if you look at the FB, it's going to rotate like that about point A, so it's going to be negative as well. And then I have the 100 Newton, and that 100 Newton, the normal distance between 100 Newton and point S is 2.5 cosine theta. And if you look at that, about point A is going to rotate it like that, so it's going to be counterclockwise, so it's going to be positive, and that would be 0. So these are the three equations we can get from our equilibrium equation. So we have these three equations, one, two, three. Now that we want to solve this equation is that we know that there are two more equations here that we know at A is on verge of motion. Therefore, FA is mu s n times n A, which is going to be 0.25 Na. And we know that the B is on verge of motion as well. Therefore, FB is also mu s NB, which is going to be 0.25 NB. So these are also the two equations we can get from the friction point, because both of them are on the verge of motion, and so we can write those equations. So therefore, if you go ahead and solve these, if you look at here, all the unknown we have 1, 2, 3, 4, and 5 unknowns. So we have 1, 2, 3, 4, 4. If we go ahead and we will look at that, if you use equation 1, 2, 3, 1, 2, 4, and 5. If we use these four equations, it gives us Na is equal 94.118 Newton, and therefore the Fa would be 23.52, and the Nb would comes out at 23.52, and Fb would be 5.88. And then if we use this in equation 3, so then if we go ahead and use equation 3, it gives us theta would be equal to 61.92 degrees. So again, one more time, because all of them are on the verge of motion, we just similar here we put the normal force and the friction, normal force and the friction, and because they are on the verge of motion, for each of the friction force we can use exactly the maximum friction forces from this equation, and we substitute that. Remember, when there is a motion, we have to get the direction of the friction correctly in order to get the solution right. So this is the case that we have if all the contacts start to move at the same time. Now let's look at another example. In this example, we want to find the maximum value of P if that does not cause any of the block A or B moving. In other words, we have two blocks. Let's get the A is 200 Newton, the B is 100 Newton, and they connected like that. And then we have this force P, and we want to see what's the maximum P can be before either of A or B starts to move. In this case, we know that one of A or B starts to move, but we don't know which one starts to move. Therefore, we have to solve the problem once, assuming A is moving completely, and calculate the P. And then the second time we calculate the whole problem assuming B is the one is moving, and find the P, and then compare two cases together. So first I will go ahead and start to draw free body diagram. So what we have free body diagram is at point C, And if I draw that point C, what I would have at the C, we have the P actually would be applying at that point. So that's the P. And then we have the force of AC, which is applying like that. So it's the FAC. And we know that that angle is going to be 30 degrees. And then we have the force CB, and we know that this angle is 45 degrees. So these are the what we have at point C. And then I will go ahead and draw the block A, see what's happening for the block A. So if I draw that A, what we have is that we know there's the external forces on that. So the forces we have, it's going to be the FAC. So it's the FAC, so it's going to be the opposite side of that. So it's going to be FAC. And this angle is going to be 30. And then we have the weight, which is the 200 newtons. So it's going to be 200 newtons is the weight. And then we have the reaction, which is going to be FA. We know that if it's going to move, if the A is going to move, it's going to go to the left. So the FA is going to be to the right. And then we have the N there. And then for the block, so that's the block A. And then for the block B, have, so for the block B, again, what we have, the external forces we have is the CB applied there. So it's going to be the CB. So it's a CB, and this angle is 45. And then we have the weight applying on that. And the weight is 100 Newton here. You know that's going to be 100 Newton. And then we would have the out there. So we have the weight 100 Newton. And then we have the reaction for this case. So this one is the NA. So here we have the NB. And we know that if the B is gonna start to move under this condition, it's gonna go to the right. So the FB is gonna go to the left. And so these are the cases we have. Now if I go ahead and start to write the all the equation we have with the entire curve. So I would start at the C. So if I go ahead and at the C, I write whatever I have at the C. Sigma fx is 0. So I would write sigma fx is 0. Therefore, FAC cosine 30 and minus FCB sine 45 gonna be 0. And then if I write the sigma Fy is 0, what I would get is that we know that the FAC sine 30 and then we have also the positive FCB sine 30 FCB sine 45 minus P is 0. So here also this one is cosine, so let me fix that. So it's going to be cosine it's a cosine 45. So So this is what we have at point C, so x and y. uh, Now if I go ahead and then I would start to write the same thing for the block A. So if I go ahead and say what we have at the A for the block A, and I would write everything that we have at the block A, again sigma fx is 0. And if you look at here, if I write the sigma of x, I have fa is positive, and then I have fac cosine 30 negative. This one is negative, and this is what I have, all I have, so it's going to be 0. And then I can write the sigma fy is 0, and for the sigma fy I have the na is positive going upward, and then I have negative fac sine 30, and then I have the weight also is moving downward negative, so it's going to 200 is going to be 0. So it's what we have at the C. And if I write what we have at the B point B, again if I write the sigma fx is 0, what I would get here is that I have the fcb cosine 45 minus fb is 0, and then if I write the sigma fy is 0, what I would get is that I have the nb is positive, and then I have negative fcb sine 45, and then I have the weight 100 is 0. So these are all the 6 equations I can write right now for in this case. So 2, 3, 4, so 5, and 6. So these are the 6 equations I can write for the entire shape. Now there's going to be cases that I want to look at that. So first of all, if you look at how many unknown we do have, we have 2 unknown here, fa here, FANA, 2 unknown also we do have here. Then we have the FAC and FCB, there's 2 also here, so 6 here, and also the P. So in total we have 7 unknown, but we have only 6 equations. And we don't know either A is gonna start to move or B is gonna start to move. So we'll do that for the case 1. So what we will do is that we will say that the case 1. In that case 1, we will assume that block A slips first. In other words, we assume that block A is the one that starts to move first. So we assume block A slips first. And then if the block A is the one that slips first, that's what we have, then we know that the FA, so FB is not moving, we don't know how much is going to be the FB, but FA is the one that on the verge of motion, so it's going to be mu S and A, so it's going to give us the mu is 0.3, so it's going to give us 0.3 and A, and it's going to be our basically the equation number 7. And then if I use all these equations together, if I use 3 and 4, and so if I look at the 3 and 4 here, so I replace FA here in 3 and 4, replace FA, so basically these 3. So if I replace FA from this equation 7 in 3 and 4, then I can solve them, and I would get these 3 would be gives me The NA would be um, 241.89. The FAC would be 83.79 Newton, and then the FA would be 72.56 Newton. And then if I use equation 1 and 2, then it gives me FBC is 102.63 Newton, and P, which is the one we are looking for, is 114.47 Newton. So basically what we have here, we assumed block A is asleep first. Because of that, this is the equation we have, this equation here, and then we replace this equation. Any place we have here, we replace it with this. Any place we have FA, we replace it with this, and we solve entire these 6 equation with these 7 equations. So we have 7 unknown, 7 equation, and we solve all the equation. So now if I go ahead and assume the another, so it's a case 1. So the second case is that the case 2 is that assume block B sleeps first. So in other words, we assume A does not moving, but A is the one actually starts to move. So if we assume A is the one that starts to move, what we have here is this time if B is going to be mu s NB, or it's going to be, in other words, going to be 0.3 NB, and this is going to be equation 8. This time we replace, in the first 6 equation, we replace FB, any place we have FB, we use that, we replace that, and then we solve these 6 equation along this equation 8 to get all the unknown we have. So in other words, if I go ahead and use 5 and 6 and 8, if we use these 3, we will get the NB would be 142.85 Newton, and then we have the FBC would be 60.60 Newton, and then we have FB would comes out as 42.85 Newton. And then if we use equation 1 and 2, this time we will get the FAC would be 49.48 Newton, and the P, which is the one we are looking at, that is the 67.60 Newton. So in this case, if you look at that, if we compare this P with this P, we know that this one is the smaller one. So basically the block B is the one that slides first, is the one that starts to move first, and therefore the maximum value we can use for the P would be in this case. So if you compare these two, the maximum is going to be the minimum of these two. So if I compare this and that, it will tells me that the P max that I can use is 67.60, because by the time that we have the 67.6 is a start to move, we never reach to that 140 that we assumed that. So remember, when we have the cases like that, that we don't know that either of the contacts might move, we have to go ahead and assume one by one, assume one of them moves, the other doesn't move, and solve the entire problem for each assumption, and then at the end compare the solution to see which one is the one that is gives us the correct answer.